So students, when we have this rolling motion, we have two kinds of motion. One is rotational motion and translational motion. So the total kinetic energy of the body which is rolling down, that kinetic energy has rotational kinetic energy as well as translational kinetic energy. We have studied the formula earlier. Kinetic energy is equal to half mv square. So now in rotational, this mass m is replaced by moment of inertia. So both plays the same role. The role of mass is that it doesn't allow the body to change its state. That is law of inertia, Newton's first law. And if a body is moving, it will not let the body stop. And if a body is at rest, it will not allow it to move unless and until some external force is applied to it. Similarly, in case of rotational motion, this I, moment of inertia, does not allow a body to rotate. And if it is rotating, it doesn't want the body to stop rotating. So same role as mass is playing in the linear motion, the same is played by moment of inertia here. And this is the linear velocity, and here it is angular velocity. And you know that angular velocity omega is equals to theta by t, that we have done in I think chapter number 4 also, last topic, uniform circular motion. So that's that omega plus translational kinetic energy, that is half m v square. So v here is center of mass. So center of mass is where we assume that the whole mass of the body is concentrated. That point is center of mass. So center of mass is for the symmetric bodies are nothing but their geometric center. That's our first question also of exercise, that what are the geometric centers. Yeah, so like sphere, its center, that's the center of mass. If suppose we have a cube, so what is the center of mass of this cube? So like x-axis, y-axis, z-axis. So moving one unit, moving half of the distance along x-axis, then half of the distance along y-axis. We have reached here. Now half of the x along z-axis. So that's the center, or the longest diagonal, they also meet at this point. So this is the center of mass of the cube. So that's so whenever an external force is applied on this body, we assume, suppose this, even I am pushing this cube, this is cubical block. So I assume that this body, suppose this has mass m, so I assume that this is this point C, this is the center of mass, and the whole force is applied on this center of mass. So I am going to study the center of motion of the center of mass, means the velocity of center of mass, acceleration of the center of mass. So it is representing this whole cube, okay, the center of mass. So in translation motion, that is half mv square. So which, because different particles have different velocities, that we have studied in the last video. You can see the last video if you have not watched, to understand rolling motion more. So now these bodies are rolling down, and here the important point is that this I will be different for different bodies. Even if the body is same but the axis of rotation is different, then also I will be different. So what are the case? We have ring. So ring is moving. So here we have the axis of rotation passing through the center. So this figure A, so the formula mr square. So for the ring, this moment of inertia is mr square for solid cylinder. So now for the solid cylinder, this is the solid cylinder, so this mr square by 2, this is the moment of inertia here. Now solid sphere, so that's formula number 8, so 2 by 5 mr square. So these are the moment of inertias. Okay, now putting this value, moment of inertia, we can also write it in the form of radius of gyration, that's mk square. So I is equals to mk square. So if you write, you can find the value of k square from here, put all of them equals to, this also equals to mk square, this also equals to mk square, this also equals to mk square. So this mk square. Now this is for the case of ring, this is for the case of solid sphere, this is cylinder, and this cylinder, and this is k for solid sphere. So what is the value of k square in case of ring? Yes, k square is equals to r square. Yes. What is k square for cylinder? So k square for cylinder is r square by 2. What is k square for solid sphere? K square is equals to 2 by 5 r square. So 2 by 5 r square is the case for the sphere. Okay, so that's k square. Now what is this angular velocity? This formula also we have done. V is equals to r omega in chapter number 4, uniform linear motion. Those who have studied note this chapter number 7, for them I am telling that this simple formula we have all done. Otherwise in chapter 7 we have derived this relation, V is equals to omega square cross r. Okay, so what is omega equals to? Omega is equals to r upon v. So that's I have put here value of omega, sorry, not r upon v upon r. So this r will come in the denominator, so it's v upon r. So that I have put, so v square by r square plus half m v center of mass square, and taking this half mass velocity of center of mass common, so I will, here it will be only 1, whereas here k square by r square. So this is the total kinetic energy of the body rolling down. Okay, now we assume the conservation of energy of the rolling body, that is there is no loss of kinetic energy due to friction. So the concept that we have studied in chapter number 6, that the work done by conservative force, because friction is not there, friction is non-conservative, so it depends. So the work done by the conservative force depends on the initial and final position. Okay, so work done by conservative force depends only on the initial and final position. So what is the initial position? Body starts rolling from here and body reach, this is the finishing line. Okay, so you can also bring the body from here to here and then from here to here also. Total work done by the gravitational force will be same in case of here and in case of here. Even the velocity will also be same here. When it will, suppose it is coming down through this, it is coming to ground, falling directly vertically or this way, even the velocities will also be the same. So here the work done is conservative work is done by the conservative force, and when the work is done by the conservative force, total energy is mechanical energy is conserved. Yes, did this concept in last chapter. Work, power, energy, mechanical energy is conserved for conservative force. So it means that change in potential energy is this potential energy lost is the gain in kinetic energy. This we already know it. We already know this concept. So how much is the potential energy lost? Everybody is not. See, this is height h. So they had the potential energy mgh, and coming to the ground they are losing that potential energy, and they are converting that potential energy. So you can write potential energy as U, or you can write it as V. So both are potential energies. So both the symbols you can use. So that is equals to the kinetic energy gained by the body. And here the kinetic energy gain is final minus initial. So here initial is 0. Okay. So the whole kinetic energy gain is your final kinetic energy, and that we can write as a K also. Okay. So that is the total energy gain. That is the kinetic energy at this point, and the energy lost is mgh. So by all the three bodies, potential energy lost mgh is equals to kinetic energy gained. So Ki is 0 because the body was at rest in the beginning. Any problem, students, still now in understanding? Concept is clear till now? Very easy concept.
Okay.
Okay. Now we know the value of K. What is the value of K? So value of now we'll be doing it for ring, and then solid cylinder, and then solid sphere. Okay. So students, in case of ring, K is equals to half m velocity of the center of mass plus 1 plus K square by R square. So that's equals to the value of, so we are supposed to find which body reaches the ground with maximum velocity. Okay, so we have to find the velocity with which the bodies are reaching the ground. So velocity is in all the three cases. Okay, so kinetic energy is equals to the potential energy loss, so that is equals to mgh, and that's equals to the kinetic energy gained. So how much is the kinetic energy gained here? So that's equals to, so if we solve this equation for all three of them, the equation will be same. Let us solve it over here. So mgh, potential energy lost, is equals to kinetic energy gained, and kinetic energy gained is equals to half m. So I'm not writing center of mass again, so it's velocity of the it's of course center of mass plus half K square by R square. So you can see that this m will be cancelling out, and you are left with V square is equals to 2gh upon 1 plus K square by R square. Okay, so 2 will go in the numerator and 1 plus K square by R square. So this is V square. So let us find this value of V square for all the three cases. So what will be V square here? So V square is equals to 2gh upon, And what will V will be equals to under the root 2gh upon 1 plus k square by r square. So if you want to write it in terms of V, you can simply write that's under the root. So 2gh upon 1 plus, what is k square in case of ring? So that's k square in case, that's equals to r square. So that's k square is equals to r square. So put the value of k square divided by r square. So k square by, so r square cancels out, and then 1 plus 1 will be 2. So 2 also cancels out. So we are left with v is equals to under the root gh. So that's the velocity of the ring. Okay. Now what's the velocity of the cylinder? So velocity in case of see students, we have ring, cylinder and sphere. Okay. So in case of solid cylinder, so what will the velocity? Under the root, same formula, 2gh upon 1 plus k square by r square. So what's k square in case of solid cylinder? That's r square by 2. So r square by 2 divided by r square. So r square will cancel out, and this is 1 plus 1 by 2. So 1 plus 1 by 2 is 3 by 2, and reciprocal of 3 by 2 is 2 by 3. So 2 by 3 multiplied by 2gh. So 2 by 3 multiplied by 2 is 4 by 3. So 4 by 3 gh is your velocity of the cylinder when it reaches the ground. Now for the sphere, that's equals to under the root 2gh upon 1 plus k square. So what's k square in case of solid sphere? That's 2 upon 5 k square, right? 2 upon 5 r square. That's the value of k square. So 2 by 5 r square divided by r square. So this comes out to be under the root. So r square will cancel out, like in this case, and 1 plus 2 by 5, that is equals to 7 by 5, and 7 by 5 reciprocal of it is 5 by 7. So 5 multiplied 2 is 10 by 7 gh. So you can clearly see this was the of the ring, velocity of the ring. So who has the greatest velocity? So of course this is this 4 by 3, this is 1 here. So under root gh is common, so here it is under the root 4 by 3, and here it is under the root 10 by 7. So 4 by 3 is 1 by 3, and 10 by 7 is 3 by 7. So of course this 1/3, so this is 0.33, and this is greater than 0.33. So it means that the sphere has the greatest velocity, and then the cylinder and ring has the least velocity. Now we have another part also, if we would like to do. Suppose the bodies have same mass, we know which body has the greatest rotational kinetic energy. So now we are talking about rotational part only. So that's your rotational part, that's your rotational part, that's your rotational part. So the rotational part is half moment of inertia into omega square. So rotational kinetic energy, rotational, is equals to 1/2 I omega square. and that we can further write as half I into omega square. You know that is V into R. Omega is V into R, V by R. So V is equal to omega R and omega is equals to V by R. So put omega is equals to V by R, so that's V square by R square. Okay, so students, let us find the rotational kinetic energy for ring, solid cylinder and solid sphere. So which body has the greatest rotational kinetic energy? So in case of ring, this K rotational is equals to half into, what is I for the moment of inertia for the ring? So moment of inertia for the ring is mr square. So that's mr square into V square by R square. So R square got cancelled out here and we get half m V square. Now kinetic energy, rotational kinetic energy of the cylinder. So for cylinder it will be, so rotational we normally write with K dash. So K dash for cylinder is equals to same half I V square by R square. So what's the value for cylinder? Moment of inertia, that is mr square by 2. So half into mr square by 2 into V square by R square. So here also R square got cancels out and we get 1 by 4 m V square. Okay, so now for solid sphere, rotational kinetic energy, that's equals to, that's for the solid sphere, so that's equals to half into I into V square by R square. And students, this comes out to be half into, what is the value of I? 2 by 5 R square. So 2 by 5 R square into V square by R square. So this R square gets cancels out and we get 2 also cancels out and we get so 2 by 5 m R square. Students, this is m here. So 1 by 5 m V square. So that's the rotational kinetic energy and when they reach the ground. So do they have the same rotational kinetic energy? No. See, their potential energy was same. Okay, their potential energy was same. The potential energy was same, mgh at the top, but their rotational kinetic energy is different. Their total kinetic energy is again same. Their potential energy is same and all that potential energy was converted into kinetic energy. So their potential energy is same, their total kinetic energy is also same, but total kinetic energy, you know, it is the sum of translational kinetic energy plus rotational kinetic energy. So they have different rotational kinetic energy and they have different translational kinetic energy. So here you can see that this one has maximum, so the ring has maximum rotational kinetic energy, means it is rotating more faster, so more revolutions per second. Okay, so students, note it down.